Hey everybody! Going down to the last talks of the day. I know you got super excited. Woo! Or not. Maybe you want this to go on for another all week. Like instead of doing RSA, you could just do B-sides. Woo! Once again, just want to thank our sponsors. Without them, this would not be possible. If you have any feedback about the conference, please go to bsides.com/feedback. If you have any specific session feedback, if you go on the schedule, click on the particular session, there's a big feedback survey button that you can click and provide feedback. We have one more raffle going on at the end of the day. It's a $150 Amazon gift card. If you just go out there, provided by Jim Alto. So go out there and put your name in the box if you want to, and we'll raffle it off at the end of the day. We are also done with everybody checking in, so we have a few extra T-shirts. So it's first come, first serve. So if you're interested in a volunteer security shirt, feel free to go and check and grab one. Now we have Martijn Grooten, a virus bulletin. He's going to be presenting Elliptic Curve Cryptography for those who are afraid of math. Please give me a warm welcome applause to Martijn.
Thank you. When I was in my late teens, my dream was to become a professional mathematician one day. And I actually went to study mathematics, and after that I worked some years as a mathematician, doing research in an area called algebraic geometry, which includes the study of elliptic curves. Life doesn't always go the way you plan it, and for some reason, kind of randomly, about 10 years ago, I find myself working for a security company. And then I discovered that these elliptic curves that I liked so much, they play an important role in cryptography. So what I'm going to do today is I'm combining my two backgrounds and I will explain how elliptic curve cryptography works, but leaving out all the boring details. I need to make some disclaimers. Firstly, I want to make clear, crypto is hard, and it takes a lot of mathematics to learn crypto, and even more to learn elliptic curve crypto. You can't do it in 25 minutes. You're not going to learn anything that you can apply tonight, tomorrow, in the next year. So sorry about that. I also want to make clear, I'm not a cryptographer. I think I understand it well enough to explain it, but I shouldn't call myself a cryptographer. And finally, to help explain, to make sure that I don't stumble over small details, I'm cutting a few corners here and there. So I apologize to the pedants in the room. Okay, every introduction into elliptic curve starts with this formula, y squared equals x cubed plus a times x plus b, and there's a prime number p, because in crypto there are always prime numbers. And I think this is unhelpful because this doesn't really matter. So please don't try to remember this formula, but do remember that there are some choices to be made. If you choose a different a or a different b or a different p, you get a different elliptic curves, and some are more suitable than others. What is important is this figure. This is what an elliptic curve looks like. You see it against the Cartesian axis, and you can see that it looks a bit funny, and it is symmetric in the horizontal axis. And on an elliptic curve there are points, and these points play an important role. As you may remember from secondary school, is the points can be represented by two coordinates. And I will assume, and that's one of these things where I'm cutting corners, that a computer represents a point by a number. So points and numbers are the same thing. So an important operation takes a point P and a point Q, and it takes the line through P and Q. And it's a fact, you just need to believe me, that's always a third point on the curve that's also on this line. And I said the curve is symmetric in the horizontal axis. So you can take the mirror image of that point, the third point, and we call this P plus Q. I cannot stress enough that this is not supposed to make any sense. Mathematics students, when they first learn this, it doesn't make any sense to them either. I'm not explaining to you what P plus Q is. I'm just defining something called P plus Q, and why this is P plus Q. It will never make sense during this talk, but it will become a little bit clear in 2 minutes. It is called point addition on a curve. There's a special case if you want to add a point P to itself to get P plus P. So what you do in this case is you take the tangent line, so the unique line that touches the curve at P. There's always unique line, and there's another extra point on the curve and also on the line. You take the mirror image of that point, and that point is P plus P. And we actually call this 2 times P. And that's point doubling. And we can combine this. We can combine point addition and point doubling by adding P and 2 times P. So we take the third point, we take the mirror image, and we get 2P plus P. And we call that, as you will expect probably, 3 times P. And we can continue, we get 4 times P and 5 times P. I'm not showing the construction here. 6 times P. And this operation is called integer multiplication. So we can add points together. We just define that, and we also define how we multiply points. And it turns out that whatever you would expect from addition and multiplication, all these rules work. There's some edge cases you have to consider, and everything falls into place. Mathematics is often very nice like that. And it means, and you don't have to remember this, the points on a curve form something called an abelian group, and that's very useful for crypto. And especially it has a very nice property, is that we can do this multiplication very fast. So if you want to go from a point P, you want to compute 100 times P, you would expect that it needs 99 steps, 99 additions, and actually you would do this in 8 steps. This may go a bit too fast for you. Don't worry about it, just believe me that you can do this in 8 steps. But if you've ever implemented fast exponentiation in a programming language, it's the very same principle. And if the numbers are even bigger, what you earn is much more. So multiplying by a billion takes 50 steps, and actually even less if you do it slightly faster. And multiplying by the enormous numbers you see in crypto takes a few hundred steps, most. On the other hand, the opposite operation is very slow. So what I mean is, if you are given 2 points on the same curve, P and Q, and you know that Q is n times P for some number n, which may be 100, which may be 15 quintillion, the only way to find this number n is to try if P, 2 times P, 3 times P, until you get Q. This is extremely slow, and if numbers are very fast, then computers simply can't do this, unless they got millions of years. So this combination of multiplication being very fast and division being very slow, this is called the discrete logarithm problem for elliptic curves, and that's the basis of all elliptic curve cryptography. Probably the most common implementation is elliptic curve Diffie-Hellman. And it's a situation where Alice and Bob want to agree on a secret key over a public channel. And I write agree in inverted commas because they don't so much agree, they actually generate some secret key together over a public channel. For example, Alice is a web browser, Bob is a web server, and they need to get a key so that they can encrypt a TLS session. So what happens is that Alice and Bob first agree publicly over a certain elliptic curve to use and a point P on that curve. And Alice chooses a large secret random number A, a very large number. And B chooses a large random number B. And they both keep these numbers secret. They don't tell them to each other. They don't share them with anyone. Now Alice computes A times P, so A times the point P. And as I said before, even if A is very large, which it will be, she can do this very fast. And she shares this answer with with Bob. And Bob computes B times P for his number B and shares this with Alice. And again, he can do this very fast. Now Alice takes this point B times P, which Bob gave her, and she multiplies it by A, by her number, and she gets A times B times P. And likewise, Bob computes B times A times P. And as I said before, mathematics is all the math that you would expect works. So A times B times P and B times A times P, they are the same number. And if you think a little bit about the discrete logarithm problem, and that's probably something you should think about later, you will know that anyone who could intercept the full communication can't crack this key. So this is a way to generate a secret key. This is used a lot in HTTPS, if your browser connects to a secure web server, and if you're very bored, you can read RFCs defining TLS and elliptic curve Diffie-Hellman in there, and you can actually find the numbers that are and the points that are shared with Wireshark. But it's a bit boring, and I didn't have time to explain it in this talk. There's a second implementation, that's random number generators. And as you probably know, computers are inherently bad at randomness. That's kind of a feature of computers. They do things extremely predictably. Now, computers can do things randomly. For example, they write something to disk and measure how long it takes, and measured in nanoseconds, taking the last 2 digits. That's kind of a random number. But that's not good enough. Computers, especially servers, they need a lot more randomness. So there's something called a random number generator. As an input, it takes some true randomness. Then it uses this true randomness, it puts it into some kind of mechanism, some algorithm. It generates some output. Part of it is usually then the true random output, and the rest of the original output is then fed back into the mechanism, and so on. And the next, I always imagine this like some machine that churns out random numbers if you input a random number once. And you can use elliptic curves for that. Remember that the discrete logarithm problem, one way to look at it is if you get a number n, and for a given point p, and you take n times p, this doesn't tell you anything about n. So it basically looks very random. So if n is a random number, then the next number, the n times p, a point / number, is again very random. So how does it work? So we start with a number n0. That's like a true random number, one that the computer has access to, but not enough. Then we take n0 times p to get a number n1. Then we take n1 times p, get another number, so point / number, n2, etc. And the output of the random number generator is just n1, n2, n3. That's just a series of random numbers. So these are random numbers. Except there's one problem. A property of random number generators is that they sometimes share the random numbers publicly, which means that an adversary sometimes has access to n1, and that's not a bug, that's a feature. But if they have access to n1, they can compute n2 and n3 because the speed is public. So if they have access to n1, they can crack the whole random number generator, which you don't want because random numbers are supposed to be unpredictable. But we can modify this algorithm a bit by using an extra point. So now we have an elliptic curve with 2 points, p and q. And we take n0, and because I'm going to formalize things a bit, it's a 32-byte seed, so 32 bytes of proper randomness. And again, we take n0 times p to get n1. But now we don't just take n1, we take n1 times q. We get another 32-byte point / number. We throw away the first 2 bytes, and we get another 30 bytes, and that's your random output. And we get again, we take n1 times p, and to get n2, and n2 times q, 30 bytes thereof, that's the next random output. And remember that the discrete logarithm problem basically means that you can't go from n1 times q to n1, so you can't crack this. And I should say, credit where credit's due, the idea of this slide and the next one to present it this way is based on a talk I once saw by Dan Bernstein, Nadia Henninger, and Tanja Lange. Now, there's an interesting fact. They said there is a large number d, so that p equals d times q. And the discrete logarithm problem says that you can't crack d. But imagine someone somehow has access to this number d. What can they do? Well, firstly, and that's unrelated to this d, they only have the 30 bytes out of 32, but there's only 65,000 possibilities. It's actually very easy because the point has to be in a curve, and it's very easy to actually get the full random output, so the full 32 bytes. And let's call this R1. So an adversary has, that's a property, has access to R1. Now, I claim that d times R1, this magic number d that imagine someone has access to it, hypothetically, is the same as n2. So why is that true? It's actually quite simple. So n2 is by definition n1 times p, and that P was P equal D times Q, as we said. You can change the order as we've already used before, so that's equal to D times N1 times Q, and N1 times Q is R1. So someone who has access to D and someone who can read R1, which is something that you assume will sometimes happen, can compute N2, and can compute the next random number and the next random number, and again has cracked the algorithm. So the $1 million question, or perhaps the $10 million question is, who knows D? Well, this is actually an algorithm that's a standard for that, and it's defined as, you can get it on the internet, and it says on the second page or so, NIST, who wrote the standard, gratefully acknowledges and appreciates contributions by Mike Boyle and Mary Beige from NSA. Oops. As most of you will probably have guessed, this is the algorithm dual EC DRBG, which has been making the news a lot in recent years. And I should also point out, I suggested that it was a good idea to use elliptic curves for random numbers. Actually, it isn't. Matt Green has written a great blog post about this. For example, it is an extremely slow algorithm. So even if you thought no one knew D, it was still a bad idea. So this made the news again recently at Juniper, and Juniper. I don't suppose you can read this, but Juniper had already publicly said, somewhat hidden on this website, that they used dual EC, but they used different points. So in its Screen OS operating system, they used different points, P and Q. And in theory, that's fine. I mean, apart from the fact that it's a very slow random number generator, but okay, I mean, that's their problem. That's not your problem as a customer. If they need to put extra memory and computing power in there, well, that's their problem. So in theory, it's okay to use different points. But in practice, you still have a potentially broken random number generator, and it turns out that someone somehow managed to change the points P and Q to different P and Q, not the P and Q that the NSA had generated, where they knew the number D, but P and Q where supposedly this adversary, China, Russia, whoever, knew the number D that had showed the relationship between these P and Q. So after dual EC DRBG, people have been wondering, rightly, is there anything else that the NSA or others have up their sleeve? And actually, it's good to point out that the curves that are used in elliptic curve Diffie-Hellman in your browser, that's called P256, that's a curve with a point on it, they use some constants that are not fully explained. And we can't fully exclude that there is a backdoor, that they weren't chosen. They were chosen by NIST again, who are very close to the NSA, that there isn't a backdoor. And there probably isn't such a backdoor. But we should really aim, as a matter of principle almost, to use curves that have only used constants that are obvious, that are not mysterious, very small numbers. If you ever see curve 25519, which Dan Bernstein invented, that's such a curve. And it's also extremely easy to implement. If you want to read more about this, and if you want to basically see the theory that the NSA has backdoored all these curves debunked, there's a great paper by Neil Koblitz and Alfred Menetes. So to round off, I hadn't mentioned this, but elliptic curve cryptography is actually a very good idea in general, because you can do it with much smaller keys. Computers are getting faster, and using RSA or standard Diffie-Hellman, you need to increase the size of your keys. 256-bit elliptic curve crypto gives about the same security as 3072-bit RSA. So it doesn't take as much CPU, it doesn't take as much memory, it doesn't take as much space to store keys. But there's also a big weakness, and is that it uses complicated maths. I mean, it's not the most complicated maths ever, but that's a kind of math that most students of mathematics will never come across. And it's often implicitly said that the fact that elliptic curve crypto uses complicated math is a strong point. And actually, I think it's a weakness. I mean, if you use crypto that you don't understand, then you basically need to trust someone else. And RSA is a lot more basic. And I think there are enough people to understand this, elliptic curve crypto, that we should use it, but we should be wary of that. You should really consider this a weakness. I've talked way too fast because I didn't think I would have 6 minutes left for questions. But there should be time for questions. I'll be speaking at another conference in town on Thursday morning about a different topic. And I'm on Twitter and email. And thank you. So, yeah?
If we consistently use well-known derivations for constants or extremely obvious constants, is that enough to at least create the correct incentives for disclosure? Like if somebody does realize that there exists a D and the D is dangerous, if we have fully public derivations, does that make us reasonably safer?
In practice, yes. And the problem isn't here that there exists a D. You can generate two random curves in a way, random points on a curve, so that we know there is a D, but you can kind of show no one can find the D this way, because my 2 points are the first two obvious points that satisfy something, and we know there is a D, but we also know we can't compute it. That's the discrete logarithm problem. Yeah.
Can you say anything about vulnerability of RSA versus ECC to quantum cryptography? I mean, quantum computing?
I was worried that someone would ask about quantum computing. I know very little about quantum computing. I think elliptic curve cryptography in general is vulnerable to quantum computing attacks. Yeah. So elliptic, yeah, almost similar in a similar way that RSA is.
I am the afraid of math part of your audience. Can you back to the slide on p times 2, p times 3?
Sorry, on the slide?
Can you go back to your early slide? Keep going.
Yeah, we're getting there.
Further.
P plus Q?
There. Here. When you draw the first line,
yes.
How do you know the angle to draw it? Is it still the same angle as the line from P through Q, and you're just moving it to a different point on the curve?
Sorry, I couldn't hear your question.
When you transition from here to the next slide.
This one?
Yes. When you draw that line,
yes.
Is it just keeping the same angle for that line and moving the starting point to a different point on the curve?
No, it is coincident that the angle is more or less the same. No, for any point on a curve, and that's a property for any curve, not even elliptic curves, there's a unique line that goes through the point, and that goes through that only goes through it once, that touches it there. It's called a tangent line. That's like, basically you take two points and you move them closer together, and you look at what happens to the line through these points. And at some point, the points fall together and there's a unique line. So,
I see. So the tangent line will change depending on where on the curve you put that
yes.
point P. Thank you.
Yeah.
Any other questions?
On the quantum computing, as far as I've been able to tell from everybody, the answer out there is that for RSA, it's definitely susceptible. And for elliptic curves, we don't know yet. Nobody's figured out how, but everybody worries because it's a short enough thing that if they do figure out how, then it'll be a problem.
About quantum?
Yeah, but right now it looks like it's probably not vulnerable.
I have been told that Shor's algorithm, which is used to crack RSA, and at least in theory it works against elliptic curves. But there are practical issues. I mean, there are people who think we might never be able to crack Summit crypto even with quantum computing. I'm not an expert. I mean, I worry about quantum computing mostly because now I understand the crypto, and with quantum computing I won't understand it anymore. Yeah, I have to trust other people, and that's freaky. Any further questions?